This session is about physical properties of amines and some chemical reactions of amines. Let me move with physical properties of amines. Physical properties of amines I am going to discuss first. As we know, amines are nothing but they are derivatives of ammonia. Hydrogens are going to be replaced by either alkyl group or aryl group. We get amines. Some amines are gaseous in state, usually lower amines, which smells like fishy. Some amines are liquid in state. Amines is the best example for colorless liquid state amines. And some amines are solid in state, they are rare. Aliphatic amines, if you consider lower aliphatic amines, they are soluble in water. Remember that if any substance or any species that is going to be soluble in water means there should be formation of a hydrogen bond. Try to know about that. So the first point what I am going to write here is lower aliphatic amines. Alkylamines you can say, lower aliphatic amines, they are soluble in water. Right now they are soluble in water, and as I told you, the aliphatic amines are soluble in water because of formation of a hydrogen bonding. You try to know about that. So there will be a hydrogen bonding in lower aliphatic amines with the water molecule. Because of that reason, the lower aliphatic amines are soluble in water. A chemical bond which is formed between hydrogen and electronegative element like nitrogen, oxygen and fluorine, that is termed as hydrogen bonding. There are two types of hydrogen bondings as we know. One is intermolecular hydrogen bonding, second one is intramolecular hydrogen bonding. If hydrogen bonding is in between two molecules, that is termed as intermolecular, isn't it? If there is hydrogen bonding within the molecule itself, that is termed as intramolecular hydrogen bonding. What happens here in case of primary amines, if you consider, so let me consider example of primary amine, that is RNH2. One hydrogen of ammonia is replaced by this alkyl group. So this is better, I can write in this fashion. So NH and H we have. So what happens when this primary amine is dissolved in water, there will be a formation of hydrogen bonding. So we have a H2O over here. So a bond between hydrogen and electronegative element you can consider, and that is how actually there will be a bond between what actually the water molecules and the hydrogen takes place, and that is termed as a hydrogen bonding. So because of this reason, what I am going to say, there will be intermolecular hydrogen bonding that causes the solubility of amines in the water. This is the reason I said lower aliphatic amines are soluble in water, whereas some higher aliphatic amines we have, they are insoluble in water. Now if you consider the solubility, right, if you consider the solubility of primary amines, the solubility is going to decrease when you increase the molar mass of primary aliphatic amines. Or I can say the alkyl group is going to be replaced by bulkier group, ethyl group, propyl group, butyl group, like that. So when you go on increasing the molecular mass, molar mass of amines, what happens? The solubility is going to decrease. What would be the reason for that? In a molecule, we have hydrophilic end and hydrophobic end, because as we know, amines are soluble in water because of hydrogen bonding, isn't it? So the part where hydrophilic in nature, attraction towards water you can call it as hydrophilic, and repulsion we call it as hydrophobic. So as long as when we are going to add the alkyl groups, in one more sense I can say the hydrophobic end is going to be increased. Hydrophobic part, the size of hydrophobic part is going to be increased, since the size of a hydrophobic part which is present in amine is going to increase when you increase the molar mass of amines. Because of that reason, what happens, the solubility of aliphatic primary amines is going to decrease. So that is how the molar mass is going to affect the solubility of primary amines. Now we will compare the solubility of amines with the solubility of alcohols. So let me consider I have alcohol and I am going to compare the solubility of alcohol with the amines. As we know, alcohols are soluble in water, and we also know that amines are also soluble in water. Both compounds are soluble in water. The reason behind that is there is a formation of hydrogen bonding, you can say. So now if you compare the solubility of alcohols as well as amines, the solubility of alcohols is more, or I can say this is more soluble. Alcohols are more soluble in water when compared to amines. The question arises, why alcohols are more soluble when compared to amines? The reason behind that, as we know, in alcohols, bond OH group is directly attached to carbon, right? So the polar nature of alcohol will be greater when compared to polar nature of amines. Polar nature arises when there is a larger electronegativity differences between the combining atoms. So in alcohols, the combining atoms have greater electronegativity differences. Because of that reason, alcohols are polar in nature. So since they are polar in nature, therefore they are more soluble in water due to again hydrogen bonding. So remember that alcohols are more soluble in nature when compared to amines. So if you consider an example of butane 1-ol and one more example of amine, that is butane 1-amine. So out of these two, so which one is more soluble? Remember that the first compound, that is butane 1-ol, that belongs to alcohol, and this example belongs to amine. Both are soluble in water. In between these two, which one is more soluble? The reason for that is, as I mentioned, butane 1-ol is nothing but alcohol that is more polar in nature when compared to butane 1-amine, which belongs to amines. So because of that reason, so butane 1-ol is more soluble in water when compared to butane 1-amine. So this is how the solubility of amines can be explained. The solubility of amines can be compared with the alcohols. Now we will see what about the boiling point of these amines. So now what I am going to write here is the boiling point order I am going to write. So the boiling point order in case of amine, so this is the primary amine and this is secondary amine and this is tertiary amine. The boiling point will be in this fashion. So the boiling point of primary amine will be more, and after you get secondary amine and after we have tertiary amine. And the boiling point will depend on the kind of force of attraction present in aqueous medium. And remember that this primary amines, there will be greater intermolecular hydrogen bonding. Why? Because in a primary amine, only one hydrogen is replaced by alkyl or amine groups, alkyl or aryl groups. Therefore, two hydrogens we have in case of primary amines. Whereas in case of a secondary, we have one hydrogen. In case of tertiary, we don't have any hydrogen here. So in a tertiary or tertiary amines, the boiling point of tertiary amine is very, very less, because we don't have hydrogen. In case of amines, if you don't have hydrogen in the amines, there is no chance of intermolecular hydrogen bonding. And whereas intermolecular hydrogen bonding is greater in case of a primary amine. Because of that reason, I can say the boiling point order in this fashion: primary amine, secondary amine and tertiary amine. So this is all about the physical properties of amines. Now we'll see the chemical properties or chemical reactions of amines. Let me write the chemical reactions. The first property I am going to consider here is basic nature of amines. So I am going to talk about basic nature of amines. ammonia is basic in nature. We know this concept. And also we know some theories that explains the acidic nature and basic nature of compounds. We know Arrhenius theory of acids and bases, Bronsted-Lowry theories of acids and bases, and Lewis theory of acids and bases. Know that ammonia is Lewis base. Any substance which donates a pair of electron is considered as base according to Lewis theory of acids and bases. Whereas any substance which accepts the pair of electron, that is considered as acid. Ammonia is considered as Lewis base since in ammonia on nitrogen we have one lone pair of electron which is easily available for protonation. That lone pair of electrons can be easily donated. Because of that reason ammonia is Lewis base. Similarly, amines are also Lewis bases. So the one very important point what I am going to write here is these amines acts as nucleophiles. These amines acts as nucleophiles and these amines acts as bases also. We'll see what would be the reason for that. So now let me consider one very simple amine, that is RNH2 primary amine. As we know, nitrogen contains a lone pair of electrons. So here I mentioned what actually the lone pair of electrons. So what I am going to say here is amines are nothing but nucleophiles. They are good nucleophiles. What would be the reason for that? As we know, electron rich species we call it as nucleophiles. Since nitrogen has 3 bond pair of electrons and it has one unshared pair of electron, or you can say lone pair of electrons, or you can say the pair of electron which is not involved in bonding. Because of that reason this species is electron rich. So any species which is an electron rich and that is considered as a nucleophiles, therefore amines are nothing but what actually they are good nucleophiles. And amines are bases, and particularly I said amines are very good Lewis base, because in amine on nitrogen we have one lone pair of electron which is easily available for donation, protonation, and because of that reason amines are nothing but they are good Lewis bases. So remember that amines depends on the reaction, it acts as a nucleophile also, it acts as a basis also. And try to remember basicity and nucleophilicity, they are not same. Nucleophilicity is different and basicity is different. When an electron rich species is going to attack on electron deficient element, and in that case the particular species acts as a nucleophile. In some reactions the same amine is going to attack on electron deficient species, electron deficient element. In that case amines behaves as a nucleophile. In some reactions the primary amines or amines, they are going to abstract proton. If you have any water or acidic substance, that is going to abstract proton from that. So in that case amines behaves as a basis. Remember that nucleophilicity is different and basicity is different, and these two properties are shown by amines because it has a lone pair of electrons. So this is the reason, based on that I can say amines are basic in nature. One more reason what I am going to say here is, let me write the particular reaction for that. RNH2, this is a primary amine, nitrogen contains lone pair of electron. When it reacts with acid, one example in general I consider hydrogen halide HX. So it has a replaceable hydrogen, or this hydrogen can be ionized, therefore this is nothing but what actually acid. So we have a species when it is going to react with acid and we will get a kind of product. I am going to write that. What is that kind of product? NH3X we are going to get. Over N you get a positive sign and over X you get a negative sign. So what happened here, this is a species and it is going to react with acid, and this is what actually, this is a salt what we are going to get. So a species is going to react with acid to produce a salt, means this original species is nothing but that is a basic in nature. So what happens actually in this reaction, these amines are basic in nature. As I said, they abstract the proton. So this is going to abstract the proton of this hydrogen halide and you are going to get RNH3X. So nitrogen, the bonding pairs will be 3. So here we have 3 and 1 4. Therefore extra we have, therefore we write plus here, and X minus we are going to write. That is the corresponding salt we are going to get. Since amines reacts with acids to form a salt, and because of this reason also I can say amines are bases. They are good basic compounds, I can say. So the basic property of amine can be better explained by pKb values and Kb values. So what are these? We'll see now. As we already know, pKb is equals to minus log of Kb, where Kb stands for dissociation constant of base. So pKb is nothing but negative logarithm to the base 10 of dissociation constant of a base. So using this equation we can get what would be the value of pKb for particular amine and what would be the value of Kb. From dissociation of the particular amine we can get the value of Kb here. So Kb helps us to know which is stronger base or weaker base, as well as pKb also helps us to know which is more basic in nature and less basic in nature, and try to know larger the value of Kb, stronger is the base. So try to know this concept, larger the value of Kb, stronger is the base. Similarly, smaller the value of Kb, smaller the value of pKb I am going to consider, and that is also stronger the base. So this point you try to know, because experimentally this helps us to know which is a stronger base when we have different kind of examples for amines. See here, larger the value of Kb, dissociation constant, if the value of dissociation constant for base, if it is larger the value we get, and that stands for stronger the base. And since pKb is equals to negative logarithm of Kb we have, because of that reason if you consider pKb values, smaller the value of pKb, and that corresponds to stronger the base. So if I consider any two amines in general A and B, and here I can write the value of pKb over here and pKb over here. So if two different pKb values we have, and how we are supposed to identify which one is a stronger base, and try to know if you consider pKb value, smaller the pKb value and stronger is the base. Instead of pKb value, if I consider Kb values, and how we predict which one is stronger, larger the value of Kb, greater or stronger will be the basic in nature of amine. So practically this pKb value and Kb value, they are going to help us whether the particular amine is stronger or weaker. Now we'll compare the basicity of alkylamines as well as arylamines with ammonia. The first I am going to consider the comparison of basicity of alkylamines versus ammonia. We'll compare these two and we'll try to figure out which one is more basic and which one is least basic I can consider. So first let me consider one simple example. In general, RNH2 we have, and this is alkylamine or alkylamine you can say, and one more I am going to consider, that will be ammonia. So now we'll compare the basicity of aliphatic amines, alkyl amines, with ammonia. As we know, these both compounds are basic in nature. Why? Because ammonia contains lone pair of electrons which is easily available for protonation. According to Lewis theory, this is basic in nature. Similarly, alkyl amines also contains a lone pair of electrons which is easily available for protonation. That is also basic in nature. The question arises, in between these two, alkyl amines and ammonia, which is more basic and which is least basic. So what I am going to say here is, here we have ammonia, but in this particular alkyl amine, nitrogen is going to be attached with the R, that is nothing but alkyl group. And remember that these alkyl groups are electron donating groups. You try to know about that one, methyl, ethyl, propyl. So these alkyl groups are very good electron donating groups. So what happens, these alkyl groups are going to donate electrons to this nitrogen. So this arrow mark I am going to write, that indicates this particular alkyl group is going to donate electron to this nitrogen, and this process or this effect we call it as the plus I effect. That is nothing but positive inductive effect. So what happens actually, if you compare carbon, of course we have alkyl group, carbon and nitrogen. Nitrogen is a more electronegative in nature. Because of that, what happens, there will be shift of electrons from less electronegative to more electronegative, and towards the more electronegative takes place, and that is termed as a plus I effect. So that we call it as positive inductive effect. So what happens, due to positive inductive effect, the alkyl group, in particular electron donating group, is going to donate or give electrons to what actually the nitrogen. So nitrogen already has a lone pair of electron, and even though this alkyl group is also going to donate electrons, so what happens, the electron density on this nitrogen increases. Try to know, because of alkyl group which is electron donating group, and due to positive I effect, what happens, the electron density on nitrogen increases. If electron density on nitrogen increases, so already we have a lone pair of electron, and electron density again increases. So we have a more number of electrons which is easily available for protonation, I can say. So since there is a more protonation of electrons which is going to be easily available, from that case I can say, so alkyl amines are more basic. So these are more basic than ammonia. So try to know what I am going to say. Aliphatic amines are more basic than ammonia. What would be the reason for that? Just I explained, aliphatic amines are more basic than ammonia due to positive inductive effect of alkyl group, which is going to increase the electron density on a nitrogen, so that more number of electrons are available on the nitrogen, which is going to be easily protonated. And because of that reason, what I am going to say here is alkyl amines or aliphatic amines are more basic in nature when compared to what actually ammonia. Remember that alkyl groups are electron donating groups, and here positive inductive effect is the reason why actually alkyl group is going to donate electrons towards this nitrogen. So we'll see one example for that one. So now I'm going to consider one particular example, CH3NH2, and I'm going to consider what is that, NH3 ammonia. Okay, so this ammonia, nitrogen contains lone pair of electrons which is easily available for protonation, basic in nature. But here we have a methyl amine. This is a methyl amine or methane amine, you can consider. So this nitrogen is directly attached to CH3, bond CH3 methyl group, which is alkyl group and which is electron donating in nature, and because of this plus I effect also, this methyl group is going to donate electrons to this nitrogen, so that the electron density on nitrogen increases, and therefore what happens, the electrons which are easily available for protonation will increase. Because of that reason also I can say this methanamine is more basic than what actually amines. So in general, remember, aliphatic amines are more basic than ammonia. Now we'll see, if we have only one alkyl group, okay, this is the primary amine what I considered, and this is how we can explain the which is more basic and which is less basic. So now we'll see what happens if the number of alkyl groups increases. So here I am going to consider one condition, that is in gaseous phase. That is going to affect a lot. Okay, so try to know in gaseous phase, so what happens to the basicity. So here I am going to consider some examples here. So let me consider example of CH3 and CH3 and CH3. Now so as we know, this is tertiary amine, this is secondary amine, and now I am going to consider primary amine. So as we know, the primary, secondary and tertiary amine depends on number of hydrogens can be replaced. So in this case all the hydrogens are replaced by methyl group, tertiary, secondary and primary we are going to get. So now we'll try to understand what about the basic nature of these three types of amines. So all these amines contains nitrogen, which is contains lone pair of electrons which is easily available for protonation. Whereas in case of tertiary amines, what happens? We have 3 alkyl groups, we have 3 methyl groups here. So this is also going to donate electron. So this methyl group is also going to donate electron, and this methyl group also is going to donate electron. So we have 3 methyl groups, all are electron donating in nature, and because of that reason, what happens? The electron density on nitrogen increases, and these electrons are going to be easily protonated. Therefore the tertiary amines are more basic, I can consider. So tertiary amines are more basic in nature when compared to secondary amine. So what happens in case of secondary amine? We have only 2 methyl groups. So this methyl is going to donate electron, and this methyl is going to donate electron. So we have only 2 methyl groups. Therefore the electron density will be less when compared to the tertiary amine. Therefore secondary amine will be the next over that. Whereas in case of a primary amine, just to observe, in case of primary amine we have only 1 methyl groups. So that is also going to donate electrons. So when you compare tertiary, secondary and primary, tertiary amine, the electron density will be greater since we have 3 methyl groups. So because of that reason, I can say in gaseous phase the basicity order of amines will be tertiary, secondary and primary, and more basic will be tertiary amine and least basic will be what actually primary amine. And remember that in all these cases the main factor is going to affect is positive inductive effect. As I mentioned earlier, that is electron donating groups we have, and that donates electron to this nitrogen, and that is considered as a positive inductive effect. So positive inductive effect is the main criteria in the gaseous phase of amines, and based on that we can explain the basic nature of different amines. So try to know that one. Aliphatic amines, if you consider, when you go on increasing the number of alkyl groups, the basicity also increases. I repeat, if you increase the number of alkyl groups, the basicity also increases because of a plus I effect. So now we'll see what happens the basicity order of amines in case of aqueous phase. So in case of aqueous phase, how we can explain the basic nature of amines? So remember that we are talking about aliphatic amines. Aliphatic amines, the basic nature will depend on plus I effect, as I explained, and it also depends on 2 more effects, and one is a solvation effect and one more is a steric effect or a steric hindrance, you can say. So 3 effects I am going to consider: plus I effect, and one more is a solvation effect, and one more is a steric effect or a steric hindrance. So plus I effect, as we know, plus I effect is mainly due to electron donating groups that donates electron, so that electron density on nitrogen increases. So because of that reason, what happens, if there is a plus I effect, the basicity is also increased. So now we'll see what happens to this solvation. Okay, so now we'll talk about how does the solvation is going to affect for the basicity, and try to know solvation, you can call it as hydration also, both are same, hydration or solvation. Since I am going to talk about aqueous phase, so amines in water, so solvation, how it is going to affect the basicity of amines, we'll see now. So now here I am going to consider one simple example, that is RNH2 primary amine. When it is dissolved in water, of course water contains H plus ions, so we have H plus ions, as I mentioned already. So ammonia, amines are basic in nature, they abstract proton. So the lone pair of electrons on the nitrogen, that is going to abstract the proton, and from that we are going to get what actually RNH3, and we get a plus sign over here. This is the cation of respective amines, I can say. So now we'll see the same cation in the presence of tertiary, secondary and primary, we'll see. So how we can explain that concept? So just observe here. Now I am going to consider the cation of primary, secondary and tertiary. So this is actually primary amine cation. Now I am going to consider the secondary. So this is the secondary cation, and I will see one more, that is of tertiary. So that depends on how many number of hydrogens you are going to replace, and this is tertiary cation. So now if you observe the structures, all these are cations of amines only, And I am going to talk about aqueous phase. Since we know amines are soluble in water because of hydrogen bonding formation. So in this case, in the primary amines, we have 3 hydrogen. So there will be a hydrogen bonding in this fashion. As we know, hydrogen bonding is represented by such kind of dashed lines. So here also we have a hydrogen bonding, and here also we have hydrogen bonding, OH2. In case of secondary amines, how I can represent hydrogen bonding? So here we have hydrogen bond between hydrogen and oxygen, and here I can mention OH2, and in this case of tertiary we have only hydrogen, one hydrogen, so OH2 I can consider. So if you compare a primary, secondary and a tertiary amine, intermolecular hydrogen bonding is greater in case of amines. Is that okay? So intermolecular hydrogen bonding is greater in case of primary amine. Why? Because we have 3 hydrogens here, therefore intermolecular hydrogen bonding is greater in case of primary amines. And what I am going to say, greater the intermolecular hydrogen bonding and greater the stability of the cation of respective amines. So this is a more stable, I am going to consider. So this is a more stable, and since greater intermolecular interaction, intermolecular hydrogen bonding, and this is more solvated and this is more hydrated, I can say. So intermolecular hydrogen bonding is greater, or I can say these compounds are more solvated, and from that case I can say this is a more stable. Whereas if you consider tertiary cation of respective amine, this is less stable and this is least solvated. Why this tertiary amine is least solvated? Because if you consider the structure of tertiary amine, we have 3 alkyl groups. What I am going to say here is 3 alkyl groups we have, the size of this cation is larger. So since it has a larger size cation, and because of that reason they are least solvated and least stable. So because of that reason, what I'm going to say here is, if you consider primary, secondary and tertiary, the basicity order with respect to solvation will be in this fashion. So first we get primary, later you get secondary, and last we get a tertiary amine, and that is the basicity order of amine with respect to solvation. Try to know. Primary amines are more basic in nature in terms of solvation, because intermolecular hydrogen bonding is greater in case of primary amines. These are more solvated, because of that reason these primary amines are more basic in nature, and that is effect of what actually the solvation effect. The one more effect apart from plus inductive effect and solvation effect, as I mentioned, and one more is steric effect. So we'll see how actually steric effect is going to affect the basicity. Steric effect, or in particular we can say steric hindrance. So first let me explain what is the meaning of a steric hindrance, steric effect. So now for that I consider one very simple example, Rn, this N. So this is the primary amine, and now I will consider secondary amine. Okay, and now here this is the tertiary amine. So all the hydrogens are replaced by what actually the alkyl groups. This is secondary and this is tertiary. So what is the meaning of a steric hindrance or steric effect is, as we know, all these amines, these nitrogen contains a lone pair of electrons. We can approach these lone pair of electrons, but remember that primary, secondary, tertiary, number of alkyl groups are not same. In case of primary, we have only one alkyl group. In case of secondary, we have 2 alkyl groups. In case of tertiary, we have 3 alkyl groups. So what I am going to say here is, approach for these lone pair of electrons is not same in case of primary, secondary and tertiary. In case of primary amines, we have only one alkylamines. We can consider it as a methyl, or you can consider it as ethyl, C2H5. So these are nothing but the bulky L groups. Size will be quite big. So since we have only one bulky group, so these lone pair of electrons can be approached very easily. Whereas in case of secondary amines, we have 2 alkyl groups, so it is a bit difficult to approach these lone pair of electrons when compared to what actually primary amine. Whereas in case of tertiary amine, if you observe, so we have 3 bulky groups, 3 alkyl groups. So if you want to approach these lone pair of electrons, it is very difficult, because these lone pair of electrons, they are surrounded by bulky alkyl groups, and therefore what I am going to say here is this is more crowded. So these tertiary amines are more crowded, whereas in case of primary amine it is the least crowded, and that effect is nothing but what actually steric hindrance. So steric hindrance is nothing but a particular, in case of amines, the lone pair of electrons, it is very difficult to approach in case of tertiary amines because we have 3 bulkyl groups. So presence of bulkyl groups makes the reactivity of amine very less, and that is concept about what actually steric hindrance or steric effect. And based on this I can say primary amine, secondary amine, tertiary amine if you consider. So primary amine will be more basic in nature when compared to secondary and when compared to tertiary, and this is the order of basicity of amines with respect to what happens here, steric hindrance. So remember that in the case of gaseous phase only plus I effect we need to consider, whereas in the case of aqueous phase you need to consider positive inductive effect as well as a solvation effect as well as a steric effect. So remember that in case of what actually gaseous phase, and this is the relation we know, tertiary will be more basic in nature, whereas if you consider the aqueous phase in a particular solvation effect, so primary will be the more basic in nature, as well as if you consider steric hindrance also, the primary is also more basic in nature. So now we'll see one example actually, and I am going to consider the examples in case of aqueous phase only. As I said, here I represented that alkyl in general, and here I represented alkyl in general. So now first we'll see what happens if R, that alkyl group, is a methyl group. If alkyl group is a methyl group, and we'll write some examples, we'll see which one is more basic in nature. So now let me write the examples for that one. So the example, if R is considered to be methyl, I am going to write here CH3 twice NH, and now CH3 NH2, and here I consider CH3 thrice N. So as we know, this is a secondary amine, and this is a primary amine, and this is a tertiary amine. Experimentally, remember that we know that in aqueous phase plus I effect, solvation effect, steric hindrance takes part. Experimentally, it is observed that if R or alkyl group is methyl group, secondary amine is more basic in nature than primary amine, and then we get what actually the tertiary amine. If R is ethyl group, so now let me consider if R, this R is ethyl group. If R is ethyl group, what would be the nature of basicity? So now let me write that if R is ethyl group, so C2H5 twice NH, and C2H5 thrice N, and C2H5 NH2. So this is a secondary amine, this is a tertiary amine, and this is a primary amine, and basic in nature in this fashion. If alkyl group, if you consider as ethyl group, and secondary amine will be more basic, then it comes tertiary, and later it comes primary. So this is how, if alkyl group is methyl, this is the order of basicity. If alkyl group is ethyl, this is the order of basicity, and these two are considered to be in aqueous phase only. So now, as I mentioned, these two are from the experimental data. In the NCERT textbook, we have a table that corresponds to pKb values, and we know that one, how pKb value and how Kb value is going to affect the basicity. So from the experimental data you can consider, this is how the ratio, or in the second degree, first degree, third degree, or primary secondary amine can be written in case of aqueous phase with respect to basicity. So now we'll analyze how experimental data is going to be correct. So now just observe here, if you consider methyl group, secondary amine will be more basic in nature, and if you consider ethyl group, secondary amine is going to be more basic in nature. So what this suggests that in these two examples, plus I effect is going to be more preferred when compared to other effects. So what happens? Secondary amine, so two alkyl groups we have, so here also we have two methyl group, and here also we have two alkyl groups. So positive inductive effect is going to account for the basicity nature of these two examples. So now in case of a methyl group, if we consider, after secondary we have a primary amine here. So since we have primary amine, and what this Example suggests us that in case of a methyl group and after secondary amine we get a primary amine because of a solvation effect. Solvation effect, because of solvation effect we know primary amines will be the greater. So in this case plus I effect is going to be considered, and here in this case what actually solvation effect is going to be considered. If you consider ethyl group as the alkyl group, of course we get a secondary as the more basic, and after that we have a tertiary. So tertiary has to be considered when compared to the primary, because this here what happens, again plus I effect is going to be considered. So what I am going to say, in case of aqueous solution you need not consider only plus I effect to predict which is more basic. You need to consider plus I effect also, solvation effect also, and steric hindrance effect also. So try to know in case of solvation, so primary will be the more stable and tertiary will be the least stable. Because of that you will get a relation like this. In case of a steric hindrance, so we have a steric hindrance in case of a tertiary, therefore that is the least. Of course we know as in case of a positive inductive effect, because these alkyl groups are electron donating in nature, and that is going to give electrons for the nitrogen, so that electron density on nitrogen increases, and because of that happens the amines are good basic in nature. Now we will compare the basicity of arylamines with ammonia. B, I am going to consider it as arylamines versus ammonia. In general, we will see one particular example, ArNH2, that stands for arylamine, and ammonia NH3. Ammonia, nitrogen contains lone pair of electrons which is easily available for protonation, therefore basic in nature. Arylamines, one hydrogen is replaced by aryl group, so this nitrogen also contains lone pair of electrons which are easily available for protonation, therefore this is also basic in nature. We will compare, if you consider ammonia and arylamine, and which one is more basic in nature we will see. So now see here we have aryl group, or I can say this is electron withdrawing group. We can consider actually benzene or phenyl group if you consider, that is electron withdrawing in nature. So electron withdrawing group it is. So since it is electron withdrawing group, so that attracts or that withdraws the electron from this nitrogen. So this effect is considered to be plus R effect, or you can call it as a plus M effect also, resonance effect, positive resonance effect, or you can call it as positive mesomeric effect also. So what happens, since there is a presence of electron withdrawing group, the nitrogen which is present in nitrogen, that is going to be withdrawn by that electron withdrawing group. So because of that what happens, so electron density on this nitrogen decreases, isn't it? So when electron density in this nitrogen decreases, and these electrons are not easily available for the protonation, so because of that reason I can say, so ammonia is more basic when you compare with what actually arylamines. So now we will see one particular example, then it will be more clear to you. So if I consider the very simple example for arylamine, that is aniline, benzene ring with NH2. So now we will compare the same thing with the ammonia. So nitrogen has lone pair of electrons, and in aniline nitrogen also has lone pair of electrons. So this benzene ring, or I can say phenyl group, is electron withdrawing group, electron withdrawing in nature. So because of a plus mesomeric effect, what happens, these lone pair of electrons are not easily available for protonation, and instead of that they are going to delocalize inside the benzene ring. So these electrons are not localized. Localized means they are not static, they are in motion. So these lone pair of electrons, they are not used for donation or protonation. Instead of that, these lone pair of electrons are involved in a delocalization inside the benzene ring. So because of that, even though this nitrogen has lone pair of electrons, they are not available for protonation. Because of that reason, I can say ammonia is more basic when compared to aniline, because in case of ammonia, here we have lone pair of electrons that can be easily protonated, whereas in case of aniline, since we have lone pair of electrons but they are involved in a delocalization, and that is considered to be the electron withdrawing group of benzene, and that process is considered to be positive M effect or positive resonance effect. And try to know this particular example is nothing but what is that, aniline. So now we'll see how actually delocalization of electrons takes place. So this I can explain by considering the resonance structures of a benzene. So now observe here, I am going to write how actually the delocalization of electron which is present on a nitrogen takes place. So this nitrogen has a lone pair of electron, isn't it? So this is going to shift in this manner. So we have a pi electron over here. So this is going to shift in this manner. So what we are going to get, we will get a one more resonating structure. So let me write that. Okay, so unchanged part I am going to write. So lone pair of electrons is going to come here. So we get double bond NH2. So it has given pair of electrons, therefore you will get a positive sign over here. So pi electron is going to shift over here. So here we are going to get what actually, negative sign. So this particular carbon or this site or this center is electron rich. Okay, so this is how we can write the resonating structure. So this kind of double-headed arrow mark indicates we are writing the resonating structures or canonical structure, contributing structures you can say. So now what happens, this electron rich center is going to shift over here and the pi electron is going to shift in this manner. So we get one more resonating structure, and how it would be. So unchanged terms I am going to write here. So NH2 plus we have. Okay, so here what happens, negative charge is going to come here, so we get a double bond here. So pi electrons is going to shift here, so we get a negative charge over here. Then what happens again, so this negative electrons will come over here and the pi electrons will shift in this manner. So I am going to write the next resonating structure here. So what we get after that particular electron shift here is, let me write the bond NH2 plus we have, and we have a double bond over here. So electron is going to shift over here, pi electrons is going to shift in this manner, so we will get a minus over here, and then again this electron will shift in this manner, pi electrons will neutralize the charge of this NH2 amine, and what we are going to get here is, we have a benzene ring, so we have a double bond over here, double bond over, double bond over. So this since has been shifted, therefore single bond NH2, and this nitrogen has lone pair of electrons. So 1, 2, 3, 4, 5. 5 resonating structures are possible for aniline. So this is how the lone pair of electrons which is present on the nitrogen in aniline is not available for protonation. Instead of that, they involve in a delocalization. So this is how actually there will be a shift of electrons, and that is considered to be delocalization of electrons. And if you observe carefully, and this is the NH2 group what we have, and this position as we know, and these two positions are nothing but ortho positions, and these two positions are nothing but a meta position, and this is the para position. So here we have electron rich center in the ortho, and here we have para, and here also ortho. So due to delocalization of lone pair of electrons which is present in aniline, I can say ortho and para positions are electron rich due to delocalization of electrons. What is going to take place in case of aniline? So this is how in aniline, even though it has a lone pair of electrons that are not available for protonation, they are used in the delocalization. Since these phenyl groups are electron withdrawing in nature, because of that the electron density on nitrogen decreases, and that's why I can say aniline is less basic when compared to ammonia. I hope now this is clear to you after writing the different resonating structures. Try to know resonating structures, the position of atoms will be same, whereas the position of electron is going to differ. You just try to know here, if you consider the first resonating structure and last resonating structure, the position of nitrogen, carbon, hydrogen will be same, whereas the position of electronic arrangement is going to be differed. So this is how the resonating structures can be drawn, and 5 resonating structures we have, and these arrow mark represents, that is nothing but the resonating structures for aniline what we are going to consider. So now this is how we can explain arylamines versus ammonia. What happens if you consider substituted arylamines? Substituted arylamines. So if you consider substituted arylamines, okay, and we have NH2, of course, when any one substituent is present. Let us assume I have electron donating group. What happens to the basicity of substituted arylamines? And what happens if I consider electron withdrawing group? So electron donating group, as we know, methyl group is very good electron donating group. Similarly, ethyl group, I can write OCH3. This is a methoxy bond, OCH3 methoxy group, and these are electron donating group. Electron withdrawing group, bond NO2 nitro group, bond CHH carboxylic acid group, and bond X halogen you can consider, and bond SO3H sulfonic acid group. So all these are electron donating group and these are electron withdrawing group. So now, as we know, the basic nature depends on availability of protonated electrons, you can say. So now what happens in case of substituted arylamines, or you can consider aniline as an example, if electron donating group is present, what happens? Of course, nitrogen has lone pair of electron, and if that is substituted by any electron donating group like this, then what happens? These groups are going to donate electrons, and what happens? The electron density on the nitrogen increases and more electrons are available for protonation. So what I am going to say, if you have electron donating group in arylamines, that is going to increase the basicity of amines. So basic nature is going to increase, basicity is going to increase if we have electron donating group as a substituent. If we have electron withdrawing group like this, so these are the electron withdrawing group, they try to withdraw the electrons which is present on the nitrogen, and what happens? The electron density on the nitrogen decreases, and what happens if electron withdrawing group is present as a substituent in case of amines? The basicity is going to decrease. So try to know about this one. What happens when electron donating group is present, and what happens electron withdrawing group is present, and that is related to how basicity can be explained in case of arylamines versus ammonia. And that is how we can link the ammonia with the alkylamines as well as the arylamines. Finally, we'll conclude with by considering very simple example. Both I considered. This is CH3NH2. This is actually methylamine, alkylamine, and I'm going to consider what is that ammonia NH3, and I'm going to consider what actually this is the arylamine, that is aniline. So now we'll see. Out of these three, all the three are basic in nature. Why? Because nitrogen contains a lone pair of electrons which is available for protonation. Therefore, all the three are basic in nature. So now we'll see which one is more basic and which one is least basic. So now we'll see about this particular NH2. That depends on electron density on the nitrogen. If electron density on nitrogen is high, and that is more basic in nature. If electron density on nitrogen is less, that is less basic in nature, I can consider. So if you consider CH3NH2, CH3 is electron donating group that donates electron, and electron density on nitrogen increases. Therefore, this is more basic in nature when compared to ammonia. Right? What happens in case of aniline? So we have a lone pair of electrons, and these lone pair of electrons, they involve in a delocalization in benzene ring, because this phenyl group is electron withdrawing group. So because of that, this is the least basic in nature. So if you consider alkyl amine and ammonia and arylamine, this is the fashion how we can write what actually the basic nature of amines. So now if I consider C2H5NH2 and that is still more basic when compared to methylamine because C2H5. Okay, so this is C2H5 means 2CS3 we have. So due to plus I effect, this is going to be more basic when you consider the example of these kind. So now you need to consider the example what have been given, and depending on that we have to see whether nitrogen is electron rich or electron deficient, and based on that you need to predict which one is more basic and which one is least basic, and that is all about the basic nature of amines. Remember that amines acts as a nucleophile also, and they are good bases also. Second property, second chemical reaction I am going to consider, that is acylation. So acylation of amines we'll see. So in general first we'll see what is actually the meaning of acylation, and later we'll see the particular example. So now what I'm going to consider, if you consider a primary amine or secondary amine, primary amine or secondary amine, if that reacts with acid chloride, that reacts with acid chloride, or that reacts with anhydride, and that may react with ester also. When a primary or a secondary amine, that may be aliphatic or aromatic, that is going to be react with the acid chloride, anhydride and ester in the presence of a base. So try to know, in the presence of a base, and we are going to get what actually N substituted alkyl amide, N substituted amide we are going to get. N substituted amide, and that is considered as acylation. So remember that when the primary or secondary amine reacts with acid chloride or anhydride or ester in the presence of a base, example pyridine you can consider, and which undergoes a nucleophilic substitution reaction and to get a product that is N substituted amide, and this kind of reaction is termed as what actually acylation. So now see here, I considered a primary and secondary amide only. So whereas a tertiary amine does not undergo acylation. Try to know this concept. Tertiary amine does not undergo acylation. Tertiary amines cannot be acylated because as we know, in a tertiary amines all the hydrogens are replaced by alkyl or aryl groups. So therefore there is no presence of hydrogen here. So if there is no presence of hydrogen, there will be no chance of acylation. Since absence of hydrogen on nitrogen atom of tertiary amine, therefore tertiary amines does not undergo what actually acylation. And remember here, in this particular example, the base like pyridine is going to be considered, because if you consider acid chloride as an example, this is strong base pyridine is going to remove hydrogen chloride which is formed. So this pyridine is going to remove the HCl which is formed when the primary or secondary amine is going to react with acid chloride, and that is the main function of base what we are going to consider, and that is how actually the definition of acylation is going to be considered. And now we'll see what is the in general reaction of acylation and what are the examples for acylation. First we'll see how does actually acylation of primary amines takes place. As I mentioned, we need to consider what actually acid chloride. So try to know, acid chloride can be represented in this fashion, C double bond O Cl. This is acid chloride. One more you can consider as a reactant. What is that? Acid chloride, and one more is anhydride. Anhydride. So anhydride can be represented in this fashion, C double bond O C double bond O, and we have a R here. So this is actually acid anhydride. Anhydride you can say. Now if you consider ester, and in case of ester, C double bond O, OR you are going to get. So this is how acid chloride, anhydride and ester can be represented. So when the primary amine and secondary amine reacts with these, any one of these, that process is considered to be acylation. So now I consider the primary amine, that is R, NH and NH2. So this is going to be considered with, I consider acid chloride. So acid chloride I am going to write in this fashion, RCOCl, and when this reaction takes place, as we know, the strong base pyridine has to be considered. And what happens during this reaction, this base is going to remove what actually hydrogen chloride which is going to be formed. In very simple, I can represent like this. When HCl is removed, and what we are going to get, so let me write here, here we are going to get RNH here, RNH, and we get COR here. So this is primary amine. So let me write for your reference, this is a primary amine, and when that reacts with acid chloride, and we are going to get what actually amide we are going to get, NHCO. So NHCO bond we have, that is considered to be amide. So this is how primary amine is going to consider. So now let me consider example of secondary amine. As I mentioned, the primary and secondary amine are going to consider the acylation. So in primary we have 2 hydrogens, in secondary we have only 1 hydrogen. What happens when that secondary amine is going to be reacted with acid chloride? So here also there will be elimination of hydrogen chloride, HCl, and what happens, the product I am going to write here. So Rn, we have a alkyl group over here, and HCl has been removed, and we are left with the COR, and that is also what actually amide. Of course, NN dialkyl amide you are going to get. So primary amines also react, secondary amines also reacts. So as I mentioned, tertiary amines won't undergo acylation. We will see why it actually won't undergo acylation. So this is how actually what happens, the tertiary amine we are going to write. And if you consider the acid chloride, or even if you consider anhydride and ester, and there is no availability of hydrogen on the nitrogen, and hydrogen is required for the acylation process, because base we are going to consider. So since there is absence of hydrogen on nitrogen, therefore there is no acylation process for what actually the tertiary amines what I am going to consider. So acid chloride as an example I considered, and the primary and the secondary amines, and how does the acylation reaction takes place. So now actually this is how we represent it in a very simple manner. The mechanism involved is, as I mentioned, there will be nucleophilic substitution reaction, and how actually this reaction carried out I am going to discuss now. And before that, I mentioned one point, that is amines are nucleophilic in nature. They are very good nucleophiles. Why they are very good nucleophiles? Because in amine, on a nitrogen we have a lone pair of electron, that is nothing but electron rich species, that is a nucleophile. And what is the main function of nucleophile? Nucleophile attacks on electron deficient element. Now the same example how we can explain using nucleophilic substitution reaction. So now just observe here how I am going to write. RNH2 primary amine I am going to consider, and now that is going to be reacted with what actually acid chloride. So acid chloride I am going to write here. So Cl C double bond O R, in general we can write acid chloride like this. So what happens when these two are going to react in the presence of a base like pyridine, and a nucleophilic substitution reaction takes place. So in between these two, which one is nucleophile, which one is electron rich species? So this primary amine is electron rich species, it has a lone pair of electron, and here we have a carbonyl carbon which is electron deficient. So what happens, this electron rich species nucleophile is going to attack on electron deficient carbonyl, and due to that what happens, the pi electron which is present in between carbon double bond oxygen is going to shift over here. So what happens after nucleophilic substitution I am going to consider here. So just see, observe how I am going to write. So R N H we have, so H I am going to write above and below, and that is going to attack on this carbonyl carbon. So therefore C I am going to write. So pi electron is going to shifted over there, so therefore I will write a minus pi electron is shifted in this fashion. So we have a Cl, I am going to consider Cl here. We have an alkyl group I am going to consider. So this amine, this nitrogen has given, therefore you get a positive charge over here. This is how actually nucleophile is going to substituted over in this carbonyl, and that is considered to be nucleophilic substitution reaction. And then what happens, here we have a electron rich, so this is going to shift in this manner. So with respect to carbon, we have a Cl group and we have R group. Usually when you compare methyl and halogen, halogens are a very good leaving group. So when the electron will come over here, this halogen is going to be eliminated, and to balance the positive charge of nitrogen, this bond is going to consider in this fashion. So what happens after this, I am going to write over here. So now observe what is going to be considered. So R we have, and nitrogen, single bond hydrogen. So this has been balanced the positive charge of nitrogen. So C, double bond O we have, Cl has been removed, and we are going to get what actually R, and the Cl which is going to be removed, and of course the bond is going to be shift here, the sigma electrons is going to shift, and H and Cl, that is going to be combined, and we are going to get Cl, or here you can write a minus HCl also. So this is how the nucleophilic substitution reaction takes place. This is actually the mechanism, but while writing, simply we can write H and Cl. This is the reaction is very as simple, just if you just look over it, but the reaction is not as simple as it seems. But if you consider the mechanism, this is how actually the nucleophilic substitution reaction takes place. This is a nucleophile, since electron rich species, since we have a carbonyl carbon which is electron deficient, so electron rich is going to attack on electron deficient, so that we are going to get the compound here, the same compound we have considered here, RNHCOR. This is the mechanism how we are going to consider. Now we'll see examples. So in general R I considered. So now we'll see some examples for that one. Okay. So primary amine, that is the CH3, NH and H I am going to consider. So when it reacts with what actually the acid chloride, ClO and ClCO, CH3. So this is methanamine we know, or methylamine. Methanamine. And in general this is acid chloride, we have CH3 group, therefore this is acetyl chloride. This is acetyl chloride, and when it reacts with base like pyridine, and what happens here, of course there will be removal of HCl. You can write the mechanism in the same fashion, but we can write in this fashion also. So what we are going to get, we get CH3, and we get NH over here, and we get COCH3. So what would be the name of this compound? This is N-methyl. See here, N-methyl we have, and this is amide, NHCO, amide, as I said, NHCO, amide these are, and 2 carbons we have, therefore I can write it as ethanamide. Ethanamide. So N-methyl ethanamide we are going to get if you consider R as a methyl group. So now aryl I am going to consider one example for that. So if you consider C6H5 phenyl group, that is NH and NH, and this is as good as aniline, isn't it? This is the aryl amine, and when it reacts with the same, that is acetyl chloride, so there will be elimination of HCl in this fashion in the presence of a base, strong base like pyridine. So what is the product we are going to get? C6H5NH. So let me write here C6H5NH we have, and COCH3. So COCH3 we are going to write. So what would be the name of this compound? N-methyl. This is the phenyl group. Therefore the name I am going to consider, this is N-phenyl, and 2 carbons we have, and that is also ethanamide, N-phenyl or ethanamide, and one well-known compound, well-known name we have for that one, and that is acetanilide. So this is how we can consider the structure of acetanilide, and this is how when acid chloride reacts with the primary amine or a secondary amine, or it may be alkyl amine or aryl amine, we are going to get the respective amides here. Remember that the mechanism involved is nucleophilic substitution reaction. What happens when amine reacts with anhydride? We'll see such example now. This is aniline. So when aniline reacts with the anhydride, so the anhydride I am going to consider here. So just see how I am writing. This is ethanoic anhydride. The name of this anhydride is ethanoic anhydride. As we know, CH3COOH, CH3COOH, ethanoic acid or acetic acid, and if you remove one molecule of water, you are going to get anhydride, and this is benzenamine or aniline you can consider, benzenamine or aniline. So what happens when these two are going to react in the presence of base like pyridine? As we know, nucleophilic substitution reaction takes place. And how does nucleophilic substitution reaction takes place? So this is nucleophile, and this nucleophile is going to attack on electron deficient carbonyl. So we have one carbonyl here over here and one carbonyl over here. You can consider anyone for the attack of the nucleophile. When the nucleophile is going to attack in this fashion, so the pi electron is going to shift over here. So now how the product I am going to consider here? So just observe how I am going to write the product. So C6H5, and we have NH2. So one hydrogen I will write above and one more hydrogen I will write below here. Bond we have, and it is going to be attacked with the carbon, and O minus we get when there is a shift of pi electrons over here, and we have CH3 I am going to consider here, and the right side we have O, and C double bond O, and we have a CH3. So here you get a positive charge for that. Then the next step, what happens? This electron is going to shift in this manner, and leaving group has to be considered, and this is the very good leaving group, and this is the bond electron is going to shift over here, and out of these two, one hydrogen is going to get over here. So now after this, what product we are going to get here? So now the product I am going to write here. Just observe how we are going to get. So C6H5 NH we get, okay, one hydrogen has been removed, and bond C double bond O we get, okay, and here we are going to get what is that, CH3, and the eliminated group is going to combine with H, and we are going to get what actually, ethanoic acid, CH3COOH, and this is nothing but the amide. So this is how when benzenamine or aniline reacts with anhydride, and we are going to get corresponding amine only. And what would be the name of this one? N-phenyl ethanamide, or the commercial name as we know, that is nothing but acetanilide, as we call it as acetanilide. So try to know, we can write acetanilide in this fashion also. So C6H5 we have, and we have NH over here, and we have a C double bond O and a CH3. So this is also acetanilide. In a molecular form we used to write in this fashion. That is nothing but, you know, N-phenyl ethanamide is the IUPAC name of that. This is how when ethanoic anhydride, in general anhydride reacts with what actually, amine. So remember that in the previous example I considered acid chloride. In acid chloride there is elimination of HCl, whereas in case of anhydride there is no Cl, there is no elimination of HCl. This is the reason I explained with the mechanism how we are going to get 1-carboxylic acid as a byproduct. One more example we will see. I will consider CH3NH2, that is the primary amine, and methanamine, methylamine you can consider, when it reacts with one kind of acid chloride, okay, and that is ClCO C6H5 I am going to consider. So CH3COCl acetyl chloride, and C6H5 we have, and this is benzoyl chloride. So try to know, this is benzoyl chloride. So when benzoyl chloride reacts with amine, especially primary amine, in the presence of base, what happens? There is elimination of HCl. So now I can write it better in this fashion for your reference. And here I can write one hydrogen over here and one hydrogen over. So this is how the HCl is going to be removed. Okay, and what we are going to get as the product? So just observe here, CH3 and NHCO C6H5. So what would be the name of this one? CH3. Therefore this is N-methyl, and this is amide. What kind of amide? This is a benzamide. So N-methyl benzamide. Remember that here we considered benzoyl chloride. When benzoyl chloride reacts with amines, we are going to get a benzamide, and this reaction we call it as benzoylation. So try to know this kind of reaction is considered to be benzoylation. So this is how, when you consider acid chloride or when you consider anhydride, of course you can consider ester also, the same kind of nucleophilic substitution reaction takes place to form what actually respective amide. From second property, that is acylation, we came to know that amines are good nucleophiles also. Some other chemical reactions we have that we'll discuss in the next session.